All right, today, by now, it should be Friday, and we should be finishing up our notes, so let's see if that's going to work or not. Okay, so there's our formula. Oops, I'm going to go back and hang out for a minute so you can make sure you get that. Okay. So ask the sub to pause it if you need to. Make sure you get them all. Alright, so it's not the 17th of November, but it's close enough, and I know it's not 2014, thank goodness, but we're going to make it work. Alright, so let's take a look. So I don't know if this dude's going to do anything. Let's see. Sometimes I have luck, and sometimes I don't. So let's see. Who knows what's going on? Nope, not a happening thing. My apologies. I will get back to class. So let's continue to move on. All right. Well, that was a bust. Okay. So we'll see the astronaut later. All right. So we're talking about momentum. And we know that the big fish is going to eat the little fish. And the mass of the big fish is 14 times the mass of the little fish. Let's look at that. Oh. All right. So the speed of the big fish is 5 kilometers an hour. And then the big fish and the little fish together can only go 4 kilometers an hour. So I know that momentum is conserved if the amount of mass involved. Come on, help me out. Increases by a factor of 5/4, and the speed at which the object moves decreases by 5/4. That's called conservation of momentum. According to the law of conservation of momentum, when the vector sum of the external forces acting on an object is 0, the total momentum of the system remains constant no matter what momentum changes occur within the system. So if you have a car crash, momentum must be conserved unless there's an outside force that gets into the system. Okay? When you play pool, conservation momentum occurs there, unless your baby brother or sister comes out and smacks the ball and changes everything. All right, for two objects interacting with each other, the conservation momentum can be expressed as m1v1 plus m2v2. So this is body 1 with its initial speed, body 2 with its initial speed, has to equal body 1 with its final speed. That's what that little prime means. m1v1 prime is momentum of body 1 after the collision. m2v2 prime is the momentum of body 2 after the collision. So v1 prime and v2 prime are the final. Okay. So if you look at this, before the collision I had mv, and this one was sitting still. After the collision, this one comes to a stop, and this one moves off with a velocity called v, because if you think about it, this mass here is simply transferring its momentum to this mass here. So this one stops, that one moves on, because the masses are equal. If I have these two headed toward each other, and they're equal masses, they're just going to pop off of each other. You've seen that in pool quite a bit. And then you have these two chasing after each other. This one is chasing after that one. Then after the collision, assuming that this one catches up with that one, they just simply get new velocity. Okay? So we'll do some math, of course. So a cart with a spring plunger runs into a fixed barrier. The mass of the cart, its velocity just before impact with the barrier, and velocity right after collision are given in figure 1. Rank the change in momentum for each cart from the greatest change in momentum to the least. Positive direction is to the right, negative direction is to the left, and a -4 is less than a -2. What's going on here? Can't be that hard. So if I look at the first situation, see if I can get on the little chart and do some writing. Okay, over here. Oops, didn't want to do that. Let's get rid of that mess. So I have a 10-kilogram mass that's moving to the left. It hits the plunger, and so it's delta P is m delta v, so 10, and then 3 minus a minus 3 is 6 times 10 is 60 for that one, and it's positive. Okay, before this 20 kilogram is moving to the left at minus 2, and then it has 0, so m delta v for this one is 20 kilograms times df, which is 0, minus a minus 20. So that one has a delta P of 40. Over here, goes from negative 1 to positive 1, so 10. Final is 1, minus a negative 1. So that would be 2 if I can do some math. So the delta P is 20. Here we have BF is 1. BI is minus 1, so 20 minus a minus, I'm sorry, let me rewrite that. So BF is 1 minus a minus 1 is 2. 2 times 20 is 40. All right, let's move on down here and see what we can figure out with these. So I have 20 and 20, so I have BF is 1 minus a minus 2. So that's 3 times 20 is 60, which happens to match A. And then I have 10 still. BF is 0 minus a negative 2 gives me a positive 2, so that's my 20. So it looks like my ranking, if I were to write it up here, it looks like A and C are going to match each other. So the greatest is going to be A, which is equal to C. And they will be greater than, okay, I have a 40 here and 40 here. So that one looks like letter D and letter E are equal. D equals E. And then I have a B, which changes by 20, and an F, which changes by 20. So there's my ranking. All right, well, let's see if that makes sense, if our little slideshow agrees with us. So I'm going to punch this, pause it if you need to. All right, let's go on down here. Ooh, I think we got it right. Okay, which of the following statements about momentum are true? And this came off of the physics classroom. Momentum is a vector quantity. We know that's true. The standard unit of momentum is the joule. No, that's energy, so nix on that one. An object with mass will have momentum, not if it's sitting still. It has to have a velocity to have momentum. An object with just moving at a constant speed has momentum. I like that one. So A and D, so far we're happy with. An object can be traveling eastward and slowing down. Its momentum is westward. Nope. Because it's m delta V. And its delta V is still eastward. So that one won't work. Momentum is a conserved quantity. The momentum of an object has never changed. I think I like that one. The momentum of any object is, all right, let's get that rid of that one because we said that one was false. Okay. So far we got good. Okay. Didn't like that one. Momentum can be changed because it can stop and lose momentum, so I was wrong there. Next. The momentum of an object varies directly with the speed. That's definitely true because it's m, v. Two objects have different mass. Moving the same speed, the more massive one definitely will have the greatest momentum because it's m, v. So if m is greater, v is the same. It has to be h. Less massive object can never have more momentum than a more massive object. That's not true. Think about a bullet and an 18-wheeler. A bullet has a teeny little mass but a huge velocity, whereas an 18-wheeler has a huge mass and a little bitty velocity. Two identical objects are moving in opposite directions at the same speed. The forward-moving object will, no. If they're identical and they have the same speed, one of them's going to be mv and one of them's going to be negative mv. Big deal. An object with a changing speed will have a change in momentum. That's true. All right. So let's move on. All right, let's see what this one says. Elastic and inelastic collisions. So if I look at collisions, elastic collision is one in which there is no loss of energy, and that's going to be considered very rare. pool table is about the closest you're going to come to that. Possibly. Okay? All right. Inelastic collision, this is what happens all the time. Objects collide and some mechanical energy is transformed into heat energy through friction. You could also have some light energy if any sparks are given off. You could have sound energy if anybody heard the crash. The animation below portrays an inelastic collision between a 1,000 kilogram car and a 3,000 kilogram truck. The before and after collision velocities and momentum are shown in the data table. Oops, let's go back. So if you look at it, here's my car. My car starts out with a mass of 1,000 kilograms. This is 3,000, so it's 3 times as massive. So if I look at the momentum before the collision, there's 20,000 here. So after I need to have 20,000, and I do because 5,000 plus 15,000 gives me my 20,000. Now if you look at it, this car is pushing this truck. Both of them are moving after the collision at 5 meters per second. So 5 times 3,000 gives me that one. 5 times 1,000 gives me that one, and they add up to 20,000. Okay? Not sure what that is. Let's go back one time. Okay, so we're good there. We've already... Okay, here's another one. Animation below portrays elastic collision between a 3,000 kilogram truck, and now the car is going to get hit by the truck. So if I look at it before the collision, 3,000 times 20 gives me 60,000. After the collision, car is no longer at rest, so watch my numbers here. It now moves at 30 meters per second because it is 1/3 the mass. It gets 3 times the velocity, and those two have to add up to my 60,000 that I had before the collision. All right, let's look at this one. So before the collision, we had 60,000 Newton seconds. After the collision, each of those had to be summed so that they added up to 60,000. All right, the animation below portrays an inelastic collision between a very massive diesel and a less massive flat car. Diesel has 4 times the mass of the freight car. After the collision, both the diesel and the flat car move together with the same velocity because he's pushing it off the track. So if you look at the mass, my diesel comes in moving at 5 kilometers an hour, and it had 40,000 kilometers per hour of momentum. After the collision, the two momentums have to add up to 40,000. And since the engine is hooked up to the flat car, they have to move off with the common velocity. So that's what's shown right there. In elastic collisions, no permanent deformation occurs. Objects bounce off of each other. If it's a head-on collision, then you're going to have, if the masses are equal, the velocities are exchanged. All right, I'm going to stop there, and then we'll get another lesson recorded.